In the last video, we mentioned the term lattice energy. Lattice energy is the energy released when a solid ionic compound forms from its gaseous ions. So notice in this series of little mini equations, it's this last step here. That's lattice energy. That's what it looks like if I'm writing it as an equation. Here I'm forming solid potassium chloride from its gaseous ions, the positive potassium ion and the negative chlorine ion. And we noted in the last video as well that lattice energy is exothermic. When I form this ionic compound, it should be a good thing for the potassium and the chlorine ions. The electron is transferred from potassium to chlorine. Both potassium and chlorine have full outer valence shells. That's very stable. That potassium chloride compound is at a lower energy level, meaning energy was released. So we should always see lattice energy as an exothermic value or a negative delta H, which is the case in this situation. We release 690 kilojoules per mole. Now, in the last video, we also mentioned that this isn't necessarily what I would think about doing if I were to form sodium chloride in the lab. In the lab, I would think about taking solid potassium in its elemental state. Potassium is a solid. Chlorine is a gas. It's a diatomic gas. So this equation given above, this is what I would think about doing in the lab. I would take a little piece of solid potassium, or I've done this with sodium. So you cut a little piece of the metal, because it's a soft metal, put it in a very safe vessel, along with some toxic yellow chlorine gas. You add a little drop of water, and that kind of activates that potassium. Remember how those alkali metals react with water? So that gives it a little boost of energy to get the reaction started, this activation energy. And then you form, tons of energy is released, but then you'll also get these little sparks and shards of solid, it's like a crusty white solid on the outside of the beaker. And that would be your solid potassium chloride. Now, to measure this lattice energy, I got to fix a few things. Number one, lattice energy is supposed to be measured from gaseous ions. I've got potassium in the solid state. So in order to get to the point where the ions are ready to form the compound, I need to get potassium from a solid state to a gaseous state. That's sublimation, right? Turning something from a solid phase to the gaseous phase. Sublimation is an endothermic phase change. You have to add energy to separate those potassium ions, or in this case atoms, from the solid phase to the gas phase. So notice that the first step here, sublimation, it's an endothermic value. We're going to need to add 64 kilojoules per mole. Well, now I've got the potassium in the right phase, it's the gas phase, but now I need to make them into gaseous ions. That's ionization energy. So the second step in this series is to take the potassium gaseous atoms, remove the electron to form the potassium ion. Ionization energy is also an endothermic value. We have to add energy to remove an electron from a positive nucleus. There is attraction within the atom. But now look what I got. Potassium ions in the gas phase. That's what I need in order to form this ionic compound. So the first two steps there were really to prepare the potassium. We turned it from the solid phase to the gas phase, and then once in the gas phase, we removed the ion. Perfect. Potassium is ready to rock and roll. Now let's fix the chlorine. It's in the right phase. It's in the gas phase. But chlorine exists as a diatomic molecule, like elemental chlorine. we want gaseous chlorine ions. Well, first thing we're going to have to do is separate those molecules. We're going to have to make chlorine atoms. Then we can add the electron to form chlorine ions. Now, if I look at this equation, it's scaled down so that we form 1 mole of potassium chloride. So we've got half a mole of potassium. That would give me 1 mole of, half a mole of chlorine. That would give me 1 mole of chlorine atoms. So we need to break those bonds. It's called bond energy. We're going to look at that in the next video. Bond energy is energy required to break a bond. It's also an endothermic value. Let's mark that in. Bond energy. Energy required to break a bond. It's an endothermic value. We have to add energy to break a bond. Chlorine wants to be bonded to another chlorine atom. In that case, they have nice full outer shells. But we want chlorine individual atoms. And another way that we can fill their outer shell is by adding an electron to those chlorine atoms. Now, the other thing that we should note too, bond energy is measured in kilojoules per 1 mole. I don't have 1 mole of chlorine molecules. I have half a mole. So if anything, this is one thing that people kind of forget. We need half of the bond energy then. So we're going to divide it in half. Now I've got my chlorine atoms in the gas phase. We're ready to turn them into chlorine ions. That's electron affinity energy. When you take the atom and you add the electron, energy is released. So this is the first time in the whole process where I see an endothermic energy value. Energy is released when I add the electron to the gaseous atom. And then bingo, here's our chlorine ion. So notice there's a lot of steps along the way. In order to form this potassium chloride solid, we have to prepare the potassium ion and the chlorine ion, which we've got now. So at this point, lattice energy is like the moment where the electron transfers from the potassium ion to the chlorine ion. And in that case, when we magically form this stable potassium chloride solid, energy is released. That's called the lattice energy. Now, to get the overall energy change for this entire process, we just add everything up. And bingo. We would release 436 kilojoules per mole of potassium chloride formed. Pretty impressive, huh? There's a couple of these in the homework, and they give you little equations like this. You could also see something like this in a multiple choice question where, yeah, there's some calculation involved, but it's basically like adding and maybe you have to divide something in half. This you could do without a calculator. We have to understand this process, though, like what all it has to take place in order to prepare those ions for the electron transfer. And that's the moment that we can form the ionic compound. It's impressive, huh? Now we should note, too, that when we form the ionic compound, we release energy. If I wanted to break that ionic compound, I would need to add 436 kilojoules per mole to separate the ions. So it's like the opposite sign of the delta H. When I form the compound, I release energy. If I wanted to separate those ions, I would have to add the same amount of energy. Okay, so here's another option. So again, there's one like this, really similar like this in the homework. And I think there's even one similar to the second one. We want to calculate the lattice energy for lithium bromide. Interesting. Okay, so very similar to the last one. Lithium is normally a solid as an element. Bromine is a diatomic gas. And in the end, I somehow want to form solid lithium bromide. The overall energy change for the formation of lithium bromide is negative 304.5 kilojoules per mole. Okay, so when I add up everything that has to take place in order to get from the lithium and bromine elements to the lithium bromide compound, here's the overall energy change. So when all this takes place, delta H is negative 304.5 kilojoules per mole. That's kind of what that delta H value represents. So they give me all the steps involved in forming lithium bromide. They may not always be in the right order. So again, like I usually say, let's fix the lithium solid first. You know, whatever comes first in the equation. Let's get that into the right phase. Lattice energy involves the formation of the ionic compound from its gaseous ions. So I need to make that lithium solid a gaseous ion. So first, let's make it a gas. So as an equation, I think of it looking kind of like this. I've got the lithium solid. I need to turn it into a lithium gas. That's sublimation. We'll just abbreviate. We'll call it E-sub. Sublimation should be an endothermic value. Yep. I would have to add 191 kilojoules per mole. Now the lithium is in the gas phase, so we can form a lithium ion. If I'm forming a lithium positive ion in the gas phase, I need to remove an electron. I'm going to form the lithium plus 1 ion in the gas phase. We're going to remove the electron. That's ionization energy. Ionization energy is also an endothermic value. Positive 520 kilojoules per mole. I need to add energy in order to remove the electron. It's very attracted to the nucleus. I mean, this is a small atom too. Lithium is ready to go. Okay, so this is what I want. I've got the positive lithium ion and I've released the electron. Now let's fix the bromine. It's in the gas phase, that's good. But right now bromine is a diatomic molecule. In order to form bromine ions, individual bromine ions, we need to start with individual bromine atoms. So let's see what we can do to fix bromine. Grab a little more room here. We've got half a mole in the balanced equation. Half a mole of diatomic bromine gas. We want to split those molecules so that we'll have a full mole of bromine atoms in the gas phase. That's called bond energy. E bond. It's an endothermic value, 193 kilojoules per mole. I have to add energy to break a bond. But again, don't forget that this was measured in kilojoules per mole. I don't have a full mole of bromine molecules. We only have half a mole in the balanced equation. So we're going to take this value, divide it in half. That's something that's often missed. Now I've got the gaseous bromine atoms, and we can add the electron to form the bromine ion. Bromine in the gas phase. We'll add the electron from lithium to form, there we go, -1 bromine ions in the gas phase. When we gain an electron to form a negative ion, that's electron affinity. I'll call it electron affinity. This is the first time where you actually see an endothermic value. Negative 324? Yeah. Kilojoules per mole. Energy is released when we form that stable bromine ion. All right, we got what we need, right? We got the lithium ion in the gas phase. We got the bromine ion in the gas phase. We're ready to wrap this thing up. Lattice energy is the energy released when I form this compound. Let's do it. We would have the lithium plus 1 ion, gas phase, plus the bromine, negative 1 ion in the gas phase, forming the solid lithium bromide. That's lattice energy, which we don't know in this case, but we do know the overall delta H. Delta H was given to us up above. Overall, this reaction releases 4.5 kilojoules per mole. Okay, so this isn't so bad. We just have to do a little math. We'll work backwards. We know the overall energy change. We'll just work backwards and calculate the lattice energy. Just don't forget, when you're plugging this in your calculator, make sure you divide that bond energy in half. That's usually the most common mistake. So let's see what we get. Let's plug this in our calculator. Lattice energy should be a negative, an exothermic. There should be energy released when I form this bond. And it is. I get negative 788 kilojoules per mole for my lattice energy. When I plug this in my calculator, so there's one thing that you can always just kind of check for, or if this were a multiple choice question and there was any positive answer listed, it's got to be wrong. Lattice energy is energy released when we form the solid ionic compound. Now again, you'll notice that the overall energy change is still exothermic, just not quite as exothermic as that lattice energy value. We actually release an overall energy change of negative 304 kilojoules per mole. But that's because a lot of the steps along the way are endothermic. And we had to add a little bit of energy to make the lithium gaseous atoms, and then we had to add a little energy to form the lithium ion and to break the bromine bonds. So there are some steps in the process that are endothermic, but you should have an overall energy change that's exothermic. We're forming a more stable compound, even though a few steps along the way require a little energy.